Discover matrix harmony through simultaneous diagonalization. This fascinating concept reveals deep connections between seemingly different matrices. In our problem today, A25, we're told to consider the matrices A as defined here, B as defined here. In part A, we're asked to verify that they are diagonalizable and that they commute. In B, find the eigenvalues and eigenvectors of A and verify that the spectrum is non-degenerate. Very important. In C, we're tasked with show that the eigenvectors of A are eigenvectors of B as well, hence simultaneously diagonalizable, and we'll see why. So to start in part A, for the check of diagonalizability and therefore commutativity, we need to verify this concept of normality, which we touched on last question. So if we remember the normality condition, the commutator of the matrix dagger with the matrix, we're going to need to see if these are Hermitian. Thankfully, they're all real matrices, so the conjugate we don't have to worry about. Now we just need to see if they are this transpose, so that's to say that they are symmetric. And in this case, they are. We switch around the main diagonal and we're all equal elements, so we're good to go there. So that being said, if we plug this into the normality condition, A dagger A minus AA dagger, we see that the Hermitian aspect of it up here puts the dagger back to A, so we see we get A here and A here. As a result, this is A squared minus A squared, so that goes to 0, so we're check, good to go. Similarly, the same thing holds for B. And what this tells us is that evidently Hermitian matrices are normal. And by the way, so are unitary matrices, except that you don't get a matrix squared, you get an identity. So either way, you're good to go for those two. And that if we see Hermitian or unitary, then we kind of know by default that they are normal and that they commute, things like that. Good stuff there. Now what we need to go ahead and to show is with both being normal and therefore both diagonalizable, if we remember that from a couple questions ago, what we need to do now is to see, do A and B commute with each other? And we need this to be true if we wish to simultaneously diagonalize them. So as we see, we know the commutator relation, AB minus BA. We see this comes together. Then we see that when we do the matrix multiplication, we get two very similar looking matrices, so similar in fact are equivalent, so we get C minus C, and we're good to go. Now, we should probably talk a little bit about why this kind of works too, or why this makes sense. So given that these were symmetric matrices, because A equaled A transpose, right? In this case, let me change colors. In this case, we know that this is going to hold because we're all real matrices. And if we remember this concept here, when I take the product of AB and I take the transpose, that's equal to the product of the transposes, but in reverse order. But if these two things are equal to their transpose, which is to say that they're symmetric, that's AB. Now, generally speaking, this right here, the product of a transpose is not necessarily equal to itself unless they do commute because of it being equal to BA right here. So we got to be careful with that. But we can kind of see here that we can get the commutativity aspect of it here thanks to the normality. So we see that AB right from underneath this leads to this. So AB does equal BA and we're good to go. So it all does kind of tie together, and we see that the symmetric, Hermitian, unitary, all these aspects of the matrices kind of build on one another, and it's very hard to keep track of them all while you're working through it. So potentially making a checklist of all these things would be beneficial because certain properties, Hermitian, unitary, they're coming through in such vigor, especially in quantum mechanics, that we kind of just want to keep them at arm's length at any time. So with that being checked off, we're good to go, and we can get on to the Eigen decomposition. So now for the Eigen decomposition, to get the eigenvalues, we need to use the characteristic equation. So recall that that was the determinant of A minus lambda I equals 0. Since we know it has to equal 0, we'll just go ahead and evaluate the determinant part of this. So here, we use the determinant to get to our characteristic polynomial. No big deal, we've seen this a couple times now. Expanding about this first row, so with the 1 minus lambda going here, plus minus plus structure, and we have 1 minus lambda crisscross, leaving us with these 4 elements to take a minor determinant. 4 here, crisscross, leaving us with these 2 and these 2, and our subdeterminant. Last element 1, crisscross, and then we're left with these 4 elements given here. Now, we can just evaluate them. Just be careful with the algebra because it does get a little intensive trying to distribute these things. But with our cofactors out front with their appropriate signs, we see that we get a second degree polynomial here with the 4, 4, 16. Distribute the 4 into that. That's where we get this first term. 4 and 1 give us -4. Clearly, the 4 and -4 cancel. 4, 4, 16. -2 minus 1. With the minus sign in between cancels out, and we get 2 plus lambda, so we're good to go. Further simplifications, all we're doing now is canceling out negative signs and then simplifying that polynomial. From there, we just distribute this 1 minus lambda into there, distribute the 4, that one's good to go. After all that's done, we see that this square here cancels with this square here. All right, fair enough, we like that. Secondly, we see that this 18 cancels with this 18, so now we can really simplify pretty quickly. As such, we don't have any square terms, we don't have any constant terms, so we have a cubic term and a linear term. We'll simplify this coefficient, brings us to 36, which if we think about it with the trace and determinant aspect, with 1 minus 2, 1, that gives us a trace of 0, so we shouldn't have a square term here if we're going through this. And we also know that without any constant terms, the determinant of this matrix A has to be 0, so we get our checks there too. Pretty cool to see all these things come together. Now furthermore, we see that both terms have a lambda in it, factored out. 36 goes to 6 squared, negative sign puts our lambda term there. What we realize here is that this is the difference of squares. So go ahead, factor that out accordingly, and this gives us our roots. Again, it has to all be equal to 0. That being said, our roots here for lambdas give us the eigenvalues, which are 0, 6, and -6. And since none of these eigenvalues are repeated, this is a non-degenerative spectrum, so we are good to go. Non-degenerate spectrum. So either way, good to go, and we can get on to the eigenvectors, which is very messy, so brace yourself. Okay. So again, to determine the eigenvectors, we substitute each of these distinct eigenvalues into the characteristic equation again, which was here. So we use the determinant to find the eigenvalues. Now we go back to this characteristic equation to find the v, the eigenvector. So plug it into the same form that we had from the matrix A minus lambda I, plug in the lambda 1 values, and our vector v1 is composed of 3 components, a1, a2, a3. From here, we can quickly see that for the first eigenvalue, which was 0, we just get the matrix back, okay? Now, what this tells us here, this whole thing, again, this 0 is a vector 0, so it's 0 for 3 components. That being said, this is a homogeneous system, homogeneous because we're equal to 0, and as such, we can solve it with Gaussian elimination. This is done via row ops. So we've seen this before in a couple videos, but after getting some feedback on it, a little more explanation as to what the row ops actually mean. Because they're a linear system of equations, we can use things like substitution or elimination to solve them. With 3 equations, 3 unknowns, substitution would be a drag, so elimination is the way to go, and that's what this method does. So a little bit more on how to read what this instruction tells us. They're telling you that for every element in row 2, we want to take it and minus 4 times the same matching element in row 1. So if we look at these two, they're in the same position of a column in different rows. So we take 4 minus 4, which is given to us, times 1, and that equals 4 minus 4, gives us 0, and that goes into the new position in row 2. So that's how we get 0 here. So if we do the same thing, minus 2 minus 4 times 4, that gives us -18. That's what we see here. And then finally, we get 4 minus 4 times 1 gives us 0. That's what we see here. So that's how we navigate these row ops, and then we just see that this reduces it all down. Once we get into the special form of reduced row echelon form, if we can, or just reduced form, then we could do a one-to-one substitution and make it really easy. So we see the first two row ops there. We see that we get a first line of all zeros down here. Perfect. That means that this last row was redundant. So the A3 is going to be our free variable. So finishing it off, we see here that we're just trying to tidy up that 18 there. And then you see here R1 minus 4R2. That gets rid of this 4 right here from here. And we get our linear equations all the way simplified down that we can. The reason why we do this is because what this tells us in the system form is that this coefficient is 1 times A1 plus 1 times A3, and all of that has to equal 0, which comes from right here. That being said, the second row tells us that 1 times A2 equals 0. So by reducing all these numbers were coefficients, and reducing the matrix like this simplifies our coefficients, and we can solve the system, as you see, very quickly. That being said, we minus this A3 over, so that gives us A1 minus A3. Again, we see here that this last row was all 0, so it was redundant. That means that we're going to have a free variable known as A3 here. That being said, this gives us a general solution of the form for the vector 1, which we are claiming is our eigenvector, had component A1, A2, A3. A1 was told to be negative A3, so we plugged it in there. A2 we found to be 0, so from right here. So we plugged it in there, and A3 we didn't have enough information on it, so it's redundant, and thus it stays put. As a result, we see that we have negative 1, 0, 1 times A3. Now this vector here is actually our eigenvector because that gives us the direction that we're going in, unnormalized of course. But since A3 is a free variable and multiplication of an eigenvector with a scalar is another eigenvector, we can set this free parameter equal to whatever we want. Since we don't like leading with negatives, we can just set A3 equal to negative 1. So that switches the sign there, and we get our first eigenvector. And we'll run the same scheme over and over again for the other two eigenvalues and get our full eigenvector set. Okay, so repeating these steps with the other two eigenvalues yields the following general solutions. And for the patrons out there, the PDF has every detail of this, but for the sake of the video, after that slow walkthrough, we can just go ahead and get to the results. Here we see that we end up with a parameterization of B3 again, but this time we had a free variable in two different locations. As a result, what we see very quickly is that pulling out that B3 leaves us with a 1, 1, 1 vector. So set B3 equal to 1, and we're good to go. Similarly, solving down for the eigenvalue for the last one, we find that we end up with our C3 being redundant again, and thus we end up with C2 equal negative C3 and C1 equal to C3. So with that, factor that out, we get that. Clearly, we're kind of stuck in this no matter what we do. We don't want to lead with the negative, so we'll just let C3 be 1, and we're good to go. But all that being said, since this is a quantum mechanics appendix, we need to normalize these real quick, and it's a slight bit of sloppy notation because we're just trying to turn these into unit vectors for regardless of whatever we set the C's or the free parameters equal to. We would have to normalize them, but this heart stays the same. That being said, take the inner product and the square root, so we're just trying to find the length of this thing. The 1, 1 from V1, 0, negative, negative, that all cancels, so we just get a root 2 as our normalization. Similarly, we see we got a root 3 for our V2, and V3, we see that we get a 6. Thank you for canceling out the negative signs. Love that. That being said, the full complete scope of this, since we did just do a lot of work, is summarized here in the box below. So for lambda 1 equals 0, the normalized vector given here. Lambda 2 equals 6, we have our normalized vector. Lambda 3 equals negative 6, we have our normalized vector. And thus we are good to go. Moving on to C, this is probably the most insightful part of this problem, since we've seen kind of eigenvectors and eigenvalues before. Now we get to see why they're important. So to demonstrate that these vectors are eigenvectors of matrix B, it is necessary to verify whether they satisfy the eigenvalue equation, meaning that I take B, multiply it by some arbitrary vector, and I get out a scalar of that same vector. In this case, the vectors are arbitrary with respect to B right now, but we found them from the eigenvectors of A. So what this shows us is that if we plug everything into this equation, for eigenvector 1, we have the normalization out here, because it's just a constant, so go ahead. We see that all these values from B, row to column, row to column, row to column, end up making, conveniently, actually pretty crazy, a 2, 0, negative 2 column vector with this normalization. So we factor the 2 out, and then we see that this is just a duplicate of the eigenvector, as you see here in the white, by a factor of 2. Therefore, we know that this vector is an eigenvector of B as well, and we're good to go. It's just going to have a different normalization since our lambda is 2. And as you see, it doesn't matter what's out front of the vector. We need to keep this as the heart of it. So regardless of what our free parameter is, we can tinker with those how we see fit. But so long as we keep this heart of the vector the same, we're good to go. Similarly, if we run this through for eigenvector 2 that we just found, 1, 1, 1, row to column, row to column, row to column, we get negative 2 on this column vector. Factor that negative 2 out, you see you get a repeat of everything from V2, so that's just a factor of negative 2 times V2, which is our eigenvalue. Pretty darn cool. Finally then, we see that B3, or B times V3, leads to 4, negative 8, 4, which is 4 over root 6 with the same column vector. So we're exactly 4 times V3. So what this says is that evidently then the eigenvalues of B are 2, negative 2, and 4. And in the PDF I verify this fact, and it is amazing that this is even the case. So with the conditions of normality leading to the commutativity aspect of these, we know that we can simultaneously diagonalize them. With the spectrum of A not being degenerate, we know that we had 3 independent eigenvectors, which was awesome. So we didn't have to employ anything like Gram-Schmidt or any other kind of tinkering with the free parameters because of that non-degeneracy. So pretty cool. And the reason why this is the case is because they share eigenvectors, we can construct the matrix P, or in this text, it's the S inverse matrix for the similarity transform, where both matrices can be diagonalized using the same similarity transforms. So since they use the same eigenvectors, making the similarity transform matrices will diagonalize them to these eigenvalues, and that's pretty darn cool. And that's why we call them simultaneously diagonalizable, because they share the same eigenvectors. So this eigen landscape is packed full of stuff that we need a whole ton of work with. Now, this simultaneous diagonalization reveals the hidden harmony between matrices A and B, showcasing how the linear algebra can uncover these deep connections and these seemingly complex systems that on the surface don't look like they're connected at all. So this is why we like using the linear algebra formalism in much of what we're trying to deal with. Very, very incredible. Okay, so not as ranty of a video as I was anticipating in my head, but that being said, a very fun one. If this video got you thinking, imagine what's coming next. Subscribe and join our community for weekly insights into the world of physics. There's so much more to uncover, and I'd love to have you along for the journey. I just want to take a moment now to thank my incredible Patreon supporters. Your support is truly the backbone of this channel. It's because of you that I'm able to keep creating these videos and diving deep into the fascinating world of physics with everyone. Your contributions make a real difference in helping me bring these concepts to life, and I'm so grateful to each of you for believing in this journey. And if anyone else is interested in supporting the channel and joining our Patreon community, you can check out the link in the description below. Together we can keep exploring the wonders of science and discovering even more amazing things. As always, thank you for watching, and until next time, stay curious.